Today I'm going to be doing the first one of probably a three-part series on on cryptography, because there's a lot out there in the world right now about how to crack Caesar ciphers and stuff like that, which you don't ever in the real world come across. Oh, I suppose you might come across it in the world, but no one's going to pay you a bug bounty for cracking a Caesar cipher. And even if you don't go into the bug bounty routes, no one's going to pay. Hopefully, no one's going to pay you to write a Caesar cipher, encryption for their website. If there is, then you probably should move. So I'm going to be looking at how we can actually crack well-designed modern cryptographic systems, and how you can design them yourself so that they don't get cracked. Now, unfortunately, before we get started on all of the fun stuff on TLS, WPA, all that stuff, we actually need to know what we're doing. And that's why this bit of cryptography often isn't taught very much, if at all. Many crypto talks, heck yes, I agree. Right, okay, so anyway, that's one. So we're gonna have to launch into, and I want to stress this is going to be made as light on the maths as possible. There's going to be very little actual maths here at all. It's going to be on information theory and computational complexity theory, and that sounds awful. Please don't click off. But it is worth getting through for the results. And once you have a basic understanding of these very simple areas, you don't just get the ability to do modern cryptography, but frankly, you can derive the whole of computer science yourself. I find that it's massively helped me with programming and everything else, just having a general idea of this in the background. Actually, we'll be getting onto the Vigenère cipher. So yes, because I'm going to be doing a bit more technical stuff today, I'd like people, if there's any questions, if anything is badly explained, you're confused with anything, whatever, just put it in the chat. I promise I won't. Okay, I don't promise I won't laugh at you. I strongly guarantee that I won't laugh at you. There we go. Within a reasonable margin of error. So let's get started on information theory. The very basics of it in a sort of less mathematical way, in a sort of more interesting way, a way that makes sort of intuitive sense. So, hopefully you can see my screen, and I haven't actually set up my pen yet. Work, frog, icon, 5. Okay. So, what do we? I suppose we all have a basic understanding of the idea of information. Clissy ciphers, basically. Okay. We have a basic understanding of what information is and what data is. If you ask, hopefully, you ask a random computer science student, they'd be able to give you a vague definition. But if we're going to try and hide it from people, we need to have a concrete explanation of what it is. I need to be able to tell you exactly how much information is in something so that I can hide it, if that makes sense. So let's take a step back and have a look at a really, really simple game, which is I am going to flip a coin, right? I'm either going to get heads or I'm going to get tails. Good so far. Now, if I predicted the result of this game, you'd be a bit surprised, right? It's a 50-50 chance. If I guess that it's a heads, you won't be shocked, but it'll be a bit of surprise. Let's quantify that and call the amount of surprise you get from me predicting one coin toss as one surprise. Sorry for my terrible handwriting. That's good. So that's a coin toss. Now, if I flip, that's a dapping emoji. Okay. So if I flip 2 coins and I predict both of them, let's say you're twice as surprised, right? That's 2 surprises. I'm going to use the singular just to annoy anyone who does grammar. So that's for 2 coin flips, right? And extending this to its natural conclusion, if I predicted n coin flips, that would be n surprises. Now, I hope none of this is beyond anyone here. If it is, please tell me to slow down. So we're quantifying surprise here as the number of coin flips required to elicit the same amount of surprise. And why am I using the idea of surprise here? Well, because after a certain number of coin flips, me predicting them all, you start to suspect something a bit fishy is going on, right? I'm not necessarily predicting it, I might have some information. Assuming the coins are actually fair, but, you know, it's somehow, maybe instead of flipping them in front of you, we've got someone else to flip them. Maybe they've secretly given me the coin flips. So there's a certain amount of if I predicted it correctly every time, there's a certain amount of information I'd be required to have to do that. So this is where the backing of it comes from, and we'll expand on that as we go through. Now, with this sort of, you know, quantized surpriseness, we could start looking at things more interesting than a single coin flip. So let's say that there was some big gambling event going on, and I predicted the correct result, and the chance of me predicting that was 1 in 65536, or 2 to the 16. That is 2 to the 16, so that's 16 times, that's 16 2 times 2 times 2, and so on. This can be seen as 16 successive coin flips. Instead of seeing it as one singular event, we can see it's me correctly predicting the result of 16 successive coin flips. It's the same amount of chance, it's the same amount of surprise you'd get from it. So from this sort of, if you bear with me, for this sort of idea of surprise, we can see this surprise, which I'm going to denote with I, of some event to be some function. Oh, I've received a message. Some function of the probability of that event, right? So flipping a coin, if we follow it through that. Oh, where did you vanish? Have I got a? Okay. So if we look here at the probability of me guessing 6, you know, a 1 in 2 to the 16 event, that's obviously 1 over 2 to the 16. Chances of me guessing, you know, 4 coin flips is 1 over 2 to the 4, which is equal to 1 over 16, and so on. So we can have, oh yes, that's it. What we have here, if I have a look at 2 coin flips, instead of modelling it as 2 successive coin flips, we can look at it as the same surprise as me guessing 1 coin flip, and then later on guessing another one. So the information you get from 2 events, A and B, is equal to the information you get from A plus the information you get from B. Assuming here that A and B are independent. If they're linked, then there's obviously some information between them. But, continuing. Now, people who've done probability in class, which I hope you all have done at least a bit, will know that the probability of A and B, if A and B are independent, are the probability of A times the probability of B. So since we have information as a function of probability, we can instead, if we write, let's say the probability of A is lowercase a, probability of B is lowercase b, we'd say that the information content of A times B, for independent A and B of course, is information of A plus the information of B. Now, many people who've done maths here will immediately be able to guess what this function is I'm talking about. But before we get onto that and before the big reveal, let me give you a bit more information about this function, because this alone is not enough to fully classify it. So, we've been looking at events that are powers of 2, or more accurately a power of a half, here. But not everything in the real world follows that. In fact, almost nothing does. If we roll a 6-sided dice, the chances of me guessing that is 1/6. And so, since we have here with our... Oh, it's crashed. Give me a second. I knew this was going to happen. Can I recover? Yes, I can. Brilliant. Okay. So, because we've been looking at the information here as a number of coin tosses, or rather, the information content of the coin toss comes with the probability of a half to the n is equal to n times the information of 1/2. Or since we've decided the information content of a coin toss is 1, that's just n. If we ask for the information content of 1/6, the result of rolling a dice, POV, yeah, I know, I'm using some really questionable software for this. Well, obviously here, n has to be more than 2, because if, what's like 1/2 to the 2 is a quarter, which is greater than a 1/6, I hope. But 1/2 to the 3 is 1/8, which is less than a sixth. So it's somewhere, the information content of a dice roll is somewhere between 2 and 3. So the question we need to ask ourselves is, how many coin flips is equivalent to rolling a dice? And, or more accurately, or in another way, we can say, how many halvings is equivalent to 1/6? And luckily, we have a function that does that. What we want is a solution to 1n equals 1/6, or generally 1/2 to the n equals a. In maths, we have a function which is called the log function. This is the opposite of the exponential function, which is a to the b. It tells you that if you it tells you that given 1/2 here, or the base here, and the result here, it tells you what this n is, and it's written like this. It's sort of the inverse of the exponential. Now, calculating this is not easy. You actually need something called a power series, and you can't actually properly approximate it. For many results, this isn't even a fraction. It's some horrific thing, a bit like, square root of 2 or pi or something, which just goes on forever. In fact, it's close. It can't even be represented as a square root or anything like that. It's usually a really nasty thing. Luckily, pretty much every software package, Python, C++, pretty much anything that isn't like assembly, will have, actually I think even assembly does have it built in, has a logarithm function built in. There's usually 3 in your language. There'll be one that's called log, which does it to a magic, which instead of using a half uses e, something which is called log 10, which will use 10 instead of a half, and something which is called log 2. Now, it doesn't have one for log 1/2, but we can cheat, because if we notice 1/2 to the m is equal to 2 to the minus 1 to the m, and by the power rules you've hopefully covered in school, that's equal to 2 to the minus m. So since we're just flipping the sign on this thing here, we can say that log base 1/2 of a is equal to minus log base 2 of a. And actually, most of the definitions you'll be given and find in the real world will be written using this minus log 2, because it's easier to write and generally easier to compute on modern systems. So let me just add a bit here. Okay, good. So we have a function here that allows us to calculate the surprisal of a specific event of some probability, like this. That's good. However, by itself, this isn't a particularly useful thing. We've just associated a number with a probability. It doesn't give us anything. So instead of looking at a specific event, let's have a look at what's called a random variable, or a whole set of events. So if we go back to a coin toss, it's not that you get heads every time you flip a coin, otherwise predicting it would be pretty easy. Instead, we look at it as multiple states. You get heads with probability 1/2, and tails with probability a 1/2. So if we take the average surprisal, we say, well, we get heads with a 1/2, so it's 1/2 times the information of heads, plus 1/2 times the information of tails. Well, since we said predicting a coin toss was pretty much by definition 1, we get 1/2 plus 1/2, which is equal to 1. And we denote this function here for, let's use C to denote a coin toss, using H, because it's the next letter. No, it's the previous letter. I should know, it's in my name. Okay. So we can write this for an arbitrary event X. We can say sum, and I know the sigma thing is irritating, but we'll get past it. Sum over every single possible thing that could happen for X, have a look at how likely it is to happen, and multiply it by the actual information of that event. And that gives you the average information, or what's known as the information entropy. Now finally, this is our first useful function here. This thing here calculates, on average, how much information a specific thing has, and therefore gives a lower bound on the amount of data you can store it in. So let me just quickly explain the difference between that. Information is the state, it's heads or tails. It's the actual thing that has happened. It's It's the results you've got. But data is the zeros and ones you're used to. So remember that, since I think I said earlier, I'm not sure if I did, that a coin toss was a single bit, because the best thing you can do with a coin toss is to 0 for heads or 1 for tails, or vice versa, so it doesn't desperately matter. That's an optimal scheme. You can see that the average information of a coin toss is 1 bit, right? The average amount you get there is 1 bit. But you could theoretically write the words "I got heads," and that would convey exactly the same information as just writing 1 if we agreed on the scheme beforehand. So the so the data here is much bigger. There's much more data, but there's the same amount of information. But we often in computers we want to try and get like the highest information density. We want to cram as much information into the smallest possible bit of data, and the information entropy gives you a way of doing that. So if I can scroll down, it tells you how bad you can do. So let's see. Let's have a slightly more complex game here, which goes like this. We flip 1 coin. If it's heads, you win. If it's tails, then we flip it 1 more time. If you get tails again, you lose. Very sad. If you get heads, then we draw. Now, if I wanted to send the result of one of these games to you, or send a stream of them to you, what is the best way we can encode it? What's the minimal amount of information it would take to store the result of one of these games, on average? Well, what we do is we say, well, if we get heads the first time, that comes with probability 1/2. And the information of that, well, it's to say it's the log of that, which is, how many halves are there in 1/2? That's 1, because it's a single coin flip. Then, for this one, getting 2 tails has a probability of 1/4, which is 1/4 times 1/4. And that happens, and that's carries 2 bits of information, because that's 2 coin tosses, or because it's 2 halvings. And for tails heads, it's exactly the same. So we get 1/2 plus 2/4 plus 2/4, which is 3 halves. So that's the information content, the entropy of this game. If I want to send you this game, it would take on average 3 halves. Now, here we have our first sort of interesting issue. You can't actually store 3 halves of a bit on computers, but on average, you can. One such scheme for doing this would be to, in the first digit, store heads or tails. So first digit, let's say 1 for heads, 0 for tails. Sorry for my handwriting. And we could write something like 0, 1. And that would be, I got tails, then heads. But if we notice, if I write heads for the first one, I don't need any more information. I've already given you the entire state. So for the ones where I get heads, which happens half the time, that would be 1/2 times 1 bit. And for the times when I get tails, that would be, which happens half the time, that'd be 1/2 times 2 bits, which is together equal to 3 halves. And that gets us this information theoretical lower bound. So just with this scheme, we don't need to bother looking for any clever compression algorithm. This is the best we can do. You might be able to, in specific cases, do better. For instance, if it's a biased coin, or you're only sending, ones where you've won, you'd be able to do better than this scheme. But given just random results of this game, you can't beat this. So there's no point looking for another scheme. But we're going to do it anyway. There's something called a Huffman tree, which you probably have come across at some point in your life. Maybe? I don't know. But it works like this. If you write down all possible events here, so we've got heads, tails, tails, and write down their probabilities, and get this sorted in order of this, you can then draw out a nice tree. Take the lowest 2 events and combine them into one big event with the sum of their 2 probabilities. Then we can strike these off and treat this as an event, their combined result as an event, and then repeat the process again. So this is an event with probability half. This is an event with probability half, but we join them because these are the lowest two. And this gives us our tree. So if we want to then encode, let's say I got heads, well, what we do is we go here and we say we record which direction we go. So we go up first. So let's have up being 1 and down being 0. Up 1, down 0. So heads would be 1. If we wanted to go for tails heads, well, the directions here would be go down 0, go up 1, 0, 1, down 0. Sorry, down. Oh, sorry. We go for tails, down, 0, 0. And you'll notice that this is actually exactly the same scheme we used up here. That's not a coincidence, I basically cheated. But given a fixed probability, if you know what the distribution of these symbols are, you cannot ever do better than this tree. This is the optimal encoding scheme. You cannot compress anything better than this, provided you know what the probabilities of each symbol are, and between messages, these probabilities aren't linked. That's it. Now, obviously, there exists a variety of different compression algorithms in the real world, and those address the two assumptions there. Usually you don't know the underlying distribution. And even more commonly, the messages aren't linked. So, messages are linked. If I are trying to compress English text, just knowing the distribution of English text does not allow you to construct, an ideal compression scheme. Because, for instance, the letter Q is almost always followed by the letter U. And the exclamation mark is usually followed by a space. Things like that mean that you could do a lot better than this bound here. Okay, so getting back onto cryptography, which is sort of where we were starting, we want to have a look at how information theory can help us in cryptography. So, first of all, let's have a look at conditional information. So this is the question: how much information is there left about X once we've worked out Y? And this is equal to the information content of X and Y minus the information content of Y. Many of you will note that this looks quite similar to the conditional probability formula given at school, which is this. And the reason for that, that should be a divide sign, whoops. And the reason why these look similar is very simple. With logs, remember how we use logs to do multiplication? Logs turn multiplication into addition and division into subtraction. Remember, if I scroll all the way back up here, that was one of our conditions here, right? We're turning multiplication, A times B, into addition. So I suppose that's not like a proper proof of why this is the case, but that's some intuition for it. I'm not going to go into like long detailed mathematical proofs because I get none of you care. Though if you want to, it can be reasonably fun to give it a go. But there's one last quantity, and this is the actual one we will use for the whole of cryptography, which is this: the mutual information of X given Y. That's asking, if I know Y, how much have I learnt about X? And that's equal to, if I can get this right, please, the information you have about the information content of X, the information entropy of X, minus the amount of information left to guess about X. Now you know Y. And I suppose that sort of, again, makes a bit of intuitive sense. But I'm just going to ask, have I gone too fast or missed anything? Or is everyone comfortable with where we are up to now? I'm going to wait for a couple of seconds because I know the chat takes a minute to go through. So let's see. Tell me if there's any questions or if you don't have any questions. God, I hate this bit. I'm not seeing any questions. Oh, all good. Okay, all Gucci. Brilliant. I will continue then. So, oh yes, and there's one last thing. We're talking about compression here. You have things like zips and stuff like that. So if I ask you this question, this is the last bit of information theory we really need to cover. Which of these sequences is more random? So that's 1, 2, 3, 4, 5, Wait, is that 7? I can't count. Yeah. Which of these sequences is more random? I'd like people to tell me this will be sequence 1, sequence 2. Which one of these do you think is random? Tell me in the chat. I'm not going to continue until I get an answer. I'm not going to continue and get an answer, so someone better write the number 1 or the number 2 in chat, or there'll be hell to pay. Go on, write the number. Someone, please. Thank you, Tom. So Tom has successfully... Now, actually, we can calculate the entropy of that. Well, let's see, we're not sure... No, the information content of that is in fact 0. So that's quite fun. Right, 1. So, wait, which of these is more random? 1. Okay, fine. So, the answer people usually give, and if I was asking a group of people, the answer people would give would be 2, right? It looks more random. But, as... I know that it's not actually, because... more random isn't something that can be applied to a single message. You have to look at the distribution. Random is quite badly quantified. We're going to quantify it here as something that your adversary, as someone who's trying to decode the message, doesn't know. Right? So that might be the result of a coin toss, which they don't know, and they're trying to work out with the information. But here, these two things can be as random as each other. But for instance, we could have, you might go, Harlan, that's not true. I can devise a better encoding scheme. I learnt about this in one of my modules. I've got 8 letters A's here, so let's devise the following scheme. If I see repeated letters, so we've got A, we can write that as 8 A's. That's good. And let's say we store this in 1 byte, and this in 1 byte. Look, we've gone down from, 8 bytes here to 2 bytes here. And with this scheme, well, we've got, 1 A, so we've got 2 A's, and then 2 B's, and then 3 A's, and then 1 B. Well, that's 1, 2, 3, 4, 5, 6, 7, 8. It's 8. So we haven't exactly lost information, but look, we beat this one. So this is much more compressible, therefore it's more random. Well, I present you with the following sequence. A, B, A, B, A, B, A, B. And we compress it using this one-length encoding again. Well, that goes to 1A, 1B, 1A, 1B, 1A, 1B, 1A, 1B. Have I lost count? No, that's good. And that's actually 16 characters long. So you've actually doubled the length here. That's rather inefficient. And in fact, on average, you will end up making things longer using this scheme. You can then go, but if I make it longer, I'll just have an extra bit on the front that tells me, actually, I didn't encode this because compressing it was longer. And that beats it. Well, it turns out that even if you do that, you're still going to be, on average, better or worse. So, not better or worse. On average, you're going to be the same or worse. Whilst for specific messages, you might do better. On average, if I give you just randomly sampled data, you're going to do better, or you're going to do worse or the same. And that applies for any compression algorithm. No compression algorithm allows you to reduce the size of random data on average. It takes advantage of common patterns. So text files, code files, picture files will always have these repeated sequences in it, which they can go for. But on average, it won't do any good. So it jumbles around the symbols so that ones that are more likely, ones which have repetitions are actually smaller. But it doesn't sort of allow you to cheat to this bound. And if you knew the underlying distribution, you could just use Huffman coding and you'd be able to make a scheme that's more efficient than any general purpose lossless compression algorithm. But that's going to go a bit more off topic, so I'm just going to leave that. Anyway, this is enough to reveal to you a secret that has been used by spies for centuries. And this is a cipher that can never be cracked. And I'm not lying here. This cipher, assuming that you do it properly, cannot ever be cracked, even by an adversary with infinite computing power who has a quantum computer, whatever. It doesn't matter, they can't crack it. And I'll describe it to you now. We have some message, M. And this message is of length, that's N, right? And then we have some K. This is our key. This is also of length N. We XOR these things together, and I hope you're all familiar with XOR. This gives you C, the ciphertext. And this is, of course, of length n. So, the question we have here is, how is this perfect? Well, let's have a look. Some adversary captures the ciphertext, and we want to know, what have they learnt about the message? Well, we came up with a nice expression for that all these years ago, which was, if I can find it, there we go, the information of x, the information entropy of x minus the information of x given y. So that's equal to HC minus HC, sorry, given m. I'm aware that my C's and brackets look very similar. Well, then even before that, we calculated that, if I've got this in the notes, yeah, we've got this expression that allows us to expand x given y. Well, this is equal to HC minus H, let's see if I get this right, HM, I think? So, HC plus HM minus HC and M. Have I got that right? I think so. So, let's evaluate this. Well, the information content of... Oh, actually, yeah, there's one last thing. Oh, yes, of course. And so, the statement I'm going to make here, which is a bit controversial, is that this is equal to H of C times H of M. And you should all be screaming at me now... Let's see. C to M, message cracked, right? You should be all screaming at me now, but C and M aren't independent. And I'm going to say they are. Because we don't know K. If you knew C and M, you'd be able to derive K. And therefore, if you knew M and K, you'd be able to derive C. I mean, that's the whole encryption process, right? So, the information content of C and M must therefore be equal to the information content of M and K. Because these two systems are the same. We can derive the whole system from either one of these two things. So I'm going to cross this out and instead use M of K. So, what's the information content of M and K? Well, that's the message length of length N, and M and K are independent. You know, K is random and M is some message. So N plus N, because they're both the length N. Oh, whoops. Oh, sorry, that's not true. So that's H of M plus N. Sorry, my mistake. We don't know what the entropy is of M. It could be a really low entropy message. It could be a really high entropy message. We don't really care. But notice here, for what we're doing is subtracting from HM, oh sorry, let me just, equals H of C plus H of M, just draw a line here, minus H of M minus H of K. That looks awful. K, there you go. So we've got these two cancel out, so this is equal to H of C minus H of K. Well, C has n bits of entropy, right? Because it's some random number XORed with whatever, it doesn't matter. We've XORed something with a random number. We're gonna have the same amount of information, so that's gonna be we haven't lost any information by XORing it. So that would be n minus, well, the key is random, so n. Great. So that is equal to 0. We have shown that knowing the ciphertext tells you absolutely bugger all about M. There's no way of working out the messages from the ciphertext. So it doesn't matter how much computation you throw at it, you will never, ever, ever be able to work out C. So, hopefully, there's a big question that's all in your minds. We've created an uncrackable code that can never be broken. Why isn't everyone using this all the time? Why are people still being hacked? And the answer is because this code is absolutely painful to use. You have to have a key that's as long as the message for every message you need to send, and the key has to be different. If you know any information about this key, all the assumptions of this start breaking down, and you start learning things about the message. So that's an absolute no-no. You have to have key material that must be kept absolutely secret and has to be perfectly randomly generated. Remember, randomness here is something your decoder can't guess or have any information about, where guessing it is just as likely as, is just as likely as just guessing at random is the same as guessing it. It's the same sort of chance of working. So, you know, if you want to, you know, you visit YouTube a lot, you probably watch gigabytes of videos. For that to be encrypted, you'd need gigabytes of data for a key that have to be stored securely and then thrown away as soon as it's used. And you have to somehow pre-agree this with Google. Even worse, Google would then need a giant database of every single person who will ever use YouTube and secret key material that can never be made public. And it gets worse because this system is something called has a property called malleability, which goes like this. Imagine I send the message 01, and I XOR it with some key. Also, that's H, right? And I'm a evil attacker, and I know that I want to flip this bit. Or even worse, I know what the value of this first bit is, and I want to set it to be 1. I don't know anything else about the rest of the message. I just want to flip that. Well, it's very simple. All I do is I go to the bit, so I want to set this to be 1, so 0 XOR 1 would be 1. And if you XOR something with 1, it flips it. And if you XOR something with 0, it keeps it the same. And that will end up being the same as the encrypted version of 1.1. And there's no way you could detect that with this scheme, right? So you can actually modify the messages very, very easily just by XORing it across. And actually, this is an attack you see in the real world, and I'll get onto that in a bit. But actually, this is something you can use on real-world production systems where people don't check the results, you know, don't check their encryption. You can just, without even having to know the key, you can just encrypt extra data in there without people being able to tell. Great. Okay, so where was I? Oh, right, that's it. So it's an awful scheme. No one wants to use it. Right, now I will go on to the second bit of this, which is on computational complexity theory. This is actually really, really simple. I'm going to just quickly glide over this, and then the talk will be done. I will then next talk be doing like actual how to hack things, but it's just important that you have the basics of this in first. So let's go. If you're doing computer science, you will have all come across the idea of ON, or something like O log n, or ON squared. You'll see these things written around, and you'll probably have a vague idea of what they mean. But actually fully understanding this is really, really simple. For some reason, they don't like properly teach it at uni, I think. Well, at least I have been told they don't properly teach it at uni. I could be incorrect in my understanding there. So, what we can do is we can define this properly in the way that's actually used by real-life researchers, which is this. We have some function f of x, or rather, let's make it f of n. Now, f here is a function that describes how long a particular algorithm takes given a certain size of input n. So this is, how do I put this? This function doesn't necessarily, this function is often quite difficult to get hold of, but that doesn't matter, as we'll see. But it assumes that such a function exists, and we want to know, is it order some g of n? So the way we write it, and I will write down the symbols, and then I'll give a much nicer explanation of what it means, is, and I may have stolen this off Stack Overflow a bit, but whatever, there exists some n for all x is less than or equal to x, f of x is less than or equal to g of x. Okay, good. That's nice. So I'm going to explain what that actually... Oh, I've got the m. Sorry. Whoops. So I'm going to explain what that means very quickly. This basically says there exists some m such that there exists some x such that for all x, where x is greater than or equal to big X, f of x is less than or equal to m times g of x, where you take absolute values. And to actually give you what that actually means, rather than just reading out symbols, we can sort of have this game, which is at some point of n. Oh, so yeah, so some x here, some capital X. After that point, all of the results of this function will be less than or equal to the same multiple of g of x. Not a different multiple each time, but the same multiple. So if I draw it as a curve, and this will be m times g of x. What I'm saying is at some point it will be below here. This we can pick any x. It doesn't have to be at the crossover point. We can pick x here. All I'm saying is there exists some capital X, and then for all x after this function stays below this one. That's all we're saying. Now, proving this can actually be really difficult, right? Sometimes it's easy, but often it can be very difficult. Because whilst for like individual functions like n squared, log n, stuff like that, if I give you like some horrific monstrosity like e to the n times n squared over n factorial, and I ask you, okay, is this greater than or equal to some multiple of e to the 2n? You're going to have no idea, right? So we actually have a condition that is sufficient but not necessary. In almost all cases it works, but there are specific cases where it doesn't work. But if it does work, if you successfully show the following thing to be true, it shows that it is order g of n, which is lim as n goes to infinity of the absolute value of f of n g of n equals c less than infinity. So let me quickly explain what this means, because this looks completely terrifying. And this is actually quite similar to a lot of some numerical analysis you may have done in computer science, which is give me some n, some capital N, right? After I'm getting confused here. Give me some error bound e, right? Actually, I'll use epsilon, because is that a 3? That's a 3, isn't it? Yeah. Give me some error bound epsilon, and we will. Wait, sorry. Let me just check. Yes. Sorry. Give me some error bound e. I'll go for e. And I want to show you that every single result of f of n over g of n after some n is within. So if I go for f of n over n minus c, sorry, so value. I want to show you that everything after n is within e of c. So after a certain number of steps, we eventually end up within any error bound you can name of c. So you name me the error bound, I can name you an n where it will be within that. Now, you might be asking, how the hell is this ever going to be easier to solve than this thing, which is comparatively a lot simpler? Well, there's two reasons. One, well, I suppose there's one big reason, which is limits here have really, really useful properties. The first one is that the limit of n to infinity of a times b, or any operation, I'm going to use. I'll use a squiggle. Actually, no, I'll use a big circle, b, right? For where circle is, that can be multiply, that can be division, that can be subtraction, addition. That can be written as lim n to infinity of a, lim n to infinity of b. That's just it can for most A's and B's for pretty much any function A and B you'll come across. This can happen. The actual thing you need is something called continuity, but that's held by pretty much any function you come across in the real world, because it's quite a useful property to have. So let's see what we have here. So we can split that up. That's good. The next bit, and this is the actually useful one, is let's say we have what's called an indeterminate form. So this would, if we just evaluated it, if we just plugged, let them both tend off to infinity, we'd end up with 0 over 0 or infinity over infinity or something like that, right? Where a result that doesn't make any sense. What we can do is take a derivative of the top and the bottom. So that would that's equal to the same limit. It's called L'Hopital's theorem. It's very nice. So if we took back this, imagine we have some function up here. Actually, let's take some evil function. Let's say I've developed Harlan's evil algorithm, and Harlan's evil algorithm for the input takes e to the n. Actually, let's say 2 to the n times n squared over n factorial. And I want to say, is this algorithm order 2 to the 2n, right? So does the time it take to run that fit within that time complexity? Well, we can just go, well, 2 to the 2n, 2 to the n. So that would go, we write the fraction as this, 2 to the n times n squared over n factorial over 2 to the 2n. And if we, I'm just going to not write limit because I'm lazy. We write 2 to the n times n squared over 2 to the 2n n factorial. Well, we can see we can cancel out some n's here. And we end up with n squared over 2 to the n times n factorial. And you could probably immediately guess that we can split this, because whilst both of them go to infinity, n squared goes a lot slower than 2 to the n and n factorial. And in fact, actually, let's see, we can cancel out one n using the n factorial, so we get n over 2 to the n times n minus 1 factorial. Suppose we're gonna now have a problem because I have to do the opposite. Damn, I shouldn't have used factorial. I made a mistake. Let's ignore factorial for a second. That's going to make us sad. I'm going to get rid of factorial because that makes our lives difficult. So yeah, let's just dupe. They cancel out. That goes away. Right, there you go. So we can now take derivatives. And if you've done this before, you'll be able to see that that goes to 1 over, let's get this right, I think log 2? Yeah, log 2 times 2 to the n, I think. Yeah. And this very clearly goes towards 0, because this grows forever, this stays forever at 1. So we've taken something which is really difficult, and just reduced it down to, does this go towards a finite number? Yes, it goes towards 0. 108 teaches it. Yes, but I hear they don't actually do limits. This is like, limits are actually a really powerful bit of maths. If you understand limits, you can basically do my entire course. But these simple tricks allow you to take what's really complex and turn it into some very, very simple things. And actually, just by knowing this formula, you can plug it into like Wolfram Alpha or something online, and it will calculate it for you. So this gives you an idea of what time complexity is. Oh yeah, and a fun fact: if sum at fx is order n, it's also order n squared, because this talks about a curve that's above it. Well, if n's above it, then n squared definitely going to be above it. So, you technically, you're taught that quicksort is, worst case is O(n) squared. Well, technically, it's also O2 to the n. Even though n squared is a lot closer fit, 2 to the n also is above it, and therefore represents a sort of an upper bound on the worst case. So, that's basically computational complexity theory. I've skipped over a couple of difficult bits of it, but that's the idea. You model the time growth with a function, and you bound it above by a multiple of another function. So if I appreciate I did rush through that, and I haven't slept properly, so I may have not covered anything fully. If there's any questions you have about that, please ask that in the chat. I'm going to keep talking, but if I see a question, I'll stop and look at it. So I'm going to present you now with a very, very simple public key crypto system. So I've shown you a private, a symmetric crypto system where both people need the same key. But as we've seen, both people needing the same key can be a bit difficult, especially on the internet. If you haven't met someone, giving them a key securely is really, really, really difficult. So, I see how everyone has deleted their message. It's 1. After I filled it's 2. Okay. So this is called Merkle's puzzles, and I think this was I'm pretty sure it was the first published crypto system that didn't require both people to have the same key. And it uses computational complexity theory. So we have Alice and Bob, as usual. And Alice wants to send Bob a message, or more accurately, wants to agree on a secret key for them to encrypt their messages with. So it could be using my perfect encryption scheme. Well, it's not my scheme. It's the scheme I just described earlier is called a one-time pad for anyone who's interested in learning it. But they want to derive a key. It could be if we're going back to Caesar ciphers, it could be the shift for the Caesar cipher. If you know what it is, it could be a 256 AES key. It doesn't really matter. They want to agree on some shared secret number without someone being able to listen. So what they do is Alice generates. Actually, listen, Bob generates. I've got the Wikipedia page up here just so I can just check that I'm not going off topic here. Bob generates some number of puzzles. Let's say 2 to the n. Right, 2 to the n because there's no n. I'm going for n. They generates n puzzles. It's like n boxes, n keys, if you will. And instead of just writing the key, they write some ID and a key. There we go. And they do this n times. So you've got ID key, blah, 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 blah. And what they do is they encrypt, they lock this away with some puzzles. So for instance, you could have, you could encrypt it normally with a very weak encryption scheme, and they have to brute force the encryption. Something like that. There's you can use what they use in blockchain, a proof of work scheme. They don't do this in blockchain, but they use something called a proof of work scheme. You could hide it behind that. There's a whole range of ways you can make it difficult to. You have to solve a puzzle before getting this information, and then publishes it publicly, so anyone can get this massive list of difficult puzzles that, when they solve it, they get a pair of an ID and a key. What Alice does is they pick one of the boxes, they crack the puzzle, so they do some maths, and then sends the ID back to Bob. Bob now knows what the key is. Alice knows what the key is because they cracked it and Bob can look it up in their table. But an outside observer would not know what ID that referred to unless they cracked the specific box. And if they start cracking all the boxes, on average they'd have to crack half of them. So whilst Alice only has to solve one puzzle, an attacker has to solve a vast number of puzzles, on average, to try and get the key. Which is nice. And this scheme can be used. And in fact, for... I suppose, let's see. I need to get the wording exactly right here. Let me check I got the exact wording right here. Yes, okay. So, for schemes of this kind, which don't involve using, like, clever maths and stuff, I don't fully understand the proof here, and what I do understand I probably can't convey easily in an accessible fashion. But this is the best scheme you can do without having to start invoking maths at things. The problem with this scheme is, again, it's really annoying to use. Because an attacker has to be... If an attacker has 10 times the power, then you need to have... you don't just need it to not be crackable in the same time. You need it to take an infeasible amount of time. So let's say that you want the puzzle to take 1 second to solve, right? That's your bound, right? Anything more than a second would slow down your system. And you want an attacker, because you can't stop them forever, they could just keep working on it forever. Let's say a safe amount of time, the message stops being secret in, shall we say, let's say 1,000 seconds. That's 20 minutes, right? So you're sending like a single command. You just don't want someone to intercept and mess with it, right? So 1,000 seconds. So already you need 1,000 secret boxes with all these puzzles in it to beat that. If the attacker has the same compute power as your client. But they don't, because they might have some more power. If they're trying to attack you, they can throw some money at it. If they get 10 computers, this now only takes 100 seconds. That's not near your bound. So you now need 10,000 boxes, right? And you can very quickly see a rough rule is 128 bits or 16 bytes is enough to be pretty much secure, right? For that's a rough rule. I'll explain it a bit later, but it's a good enough bound. 256 if you pound or 32 bytes, but 16 bytes is usually enough for security. So we're saying 16 bytes 10,000 times, and we've got all these puzzles. So we've got an ID, so that's 16,000. That's 16, 32 plus some puzzle on the top, which would probably be, let's say, another 16 bytes. Well, that's 48 times 10,000. That's 48 kilobytes you now need to send. And this scheme's now, and if you're only sending a bit of information, this is a horrific waste of time. And once they use the box, you sort of have to throw it away. It's a bit of a waste. And in the real world, these ratios aren't realistic. If I'm logging in something with my password, I'm going on to, how to commit evil acts and kick puppies.net. And I don't want anyone else knowing that I frequently visit the forums of this website within my lifetime. Right, let's see. Let me just do the calculation here. Let's say you're going to live for another, let's be optimistic here, 80 years. Right, you don't want anyone finding out in the next 80 years. That is, if I use a calculator here, yeah, that is about 1 billion seconds, give or take. Right, so that's 1 billion boxes. And that's a gigabyte you now have to publish and check through. And this is assuming, again, that they have the same amount of power. Assuming you're going against an adversary who's really dedicated, and there's 100 times the power, you're talking about hundreds of gigabytes, even into the terabytes for your key. And this becomes really, really impractical very, very quickly. So the actual slowdown for the time complexity, for the size of your key, if you make it, the number of keys, it's order n, and for, let's say the puzzle is, increases linearly with length, this is the bound here is n times n, assuming these are roughly equivalent. This is rough. I'm talking very hand wavy here. You can do this more formally. This is roughly order n squared of security. So whilst growing like n squared sounds really impressive, it gets very impractical very quickly. What we want is something close to exponential, where doubling. So here, doubling the key size only makes it 4 times harder. What we want is if you double the key size, it makes it it squares the difficulty, right? Because that means that it's very, if something is crackable, you need to make it a bit longer, and boom, it becomes completely uncrackable. And in fact, that's what RSA does. RSA, not quite, but close enough, has exponential time complexity. The actual thing is like some horrific equation I don't actually understand. But it's roughly 2 to the n. It used to be that people used 512-bit RSA, and that got cracked really quickly. So they used 1024-bit, and that got cracked pretty soon after that. Now they use 204-8-bit. That can't really be cracked unless, well, I suppose I'm not supposed to say unless you're the NSA, but unless you're the NSA, you can't crack it. And if they did, if I make it 4096, that makes the time taken to fix it, assuming this complexity bound is correct, square. Which, if someone's just about managed to crack 204-8-bit, there's no chance they're ever going to be able to crack 496-bit. Just adding a single bit doubles the time complexity, right? It's not actually 2 to the n, it's something else, but whatever. It's slightly below 2 to the n. But remember how I said 2 to the n is an upper bound, so whatever. Anyway, that is, I think, pretty much everything I want to go in the theory. After this talk, I'm going to start launching into, actual proper crypto systems, which are used in the real world, not Merkel's puzzles, but actual things that real people use, the pitfalls they have with them and how you can suck the information out of them, and also how to build systems which it's harder to break. Actually, but I suppose I'll leave you with what's known as Schneer's law. I'm not sure how to pronounce the name, but Bush Schneer, however it's pronounced, is a sort of has constructed cryptographic standards. He's a big sort of cryptographer. He has a blog, all those things. But he has a big famous rule, which is any person can invent a security system so clever that she or he can't think of how to break it. And that's a sort of a double-edged thing. It's very common you see people looking up cryptography, maybe even researching it and understanding it, and then designing their own system that they can't work out how to break, but then someone else works out how to break it almost immediately. And that's why you shouldn't construct your own crypto systems. Whenever possible, use somebody else's one which has been peer-reviewed and trusted for years. I mean, things like AES and SHA-256 have been around longer than me, and haven't had any significant improvements made on them. Not for lack of trying. Anyone who manages to crack those ciphers not only could, hack the planet, but also could get a job working pretty much wherever they like for an amazing contribution to cryptography. So, use systems that are in place that have been peer-reviewed and trusted for years and years in your systems whenever possible. Whilst constructing toy cryptographic systems is fun, you need to be really careful doing it in the real world. I mean, the screw-ups like this commonly happen even on sort of company scale, right? I'll leave that to the next talk. I'm going to head over to Discord now. I hope that wasn't too confusing. Oh yes, any questions? Type in the chat if you've got any questions, please. And I'm happy to go over anything that I've gone through or anything that's confused you. Please feel free to ask. If you want, I won't name and shame you. If for some reason you feel like your question is horrifically embarrassing, it almost certainly isn't. I actually had to recheck some of this stuff before I gave the talk. I actually had been using the limit one before I noticed that a definition of big O before realizing that actually the other one was the definition. Like, trust me, you can say anything like, don't forget to like, comment, and subscribe. Yes, that's important. It's like, comment, and subscribe. We don't like. But yeah, please, any questions? Please give questions. Talk for my man, lovely maths. Thank you. I try to be light on the maths as possible. If anyone wants the maths, I'm very happy to go into any level of detail about the maths they want me to go into. I'm actually a bit more comfortable with the maths than the sort of general arm wavy description. So I'm very happy to do the maths if anyone's interested in that. But I get that most of you didn't sign up to do a maths degree because you didn't want to listen to long hour-long proofs. Though I would love to give them. Let's see. Any other questions? Okay, I'm gonna go into a public channel in Discord. I've muted my desktop so that I can hear you, but the recording won't. So if anyone's interested in asking questions but don't want it repeated again, I'm very happy to do that. So I'm gonna go over to the voice chat now. Hello. Do you have questions? Lost Posh. Was this the Order N, Order M stuff with Merkel's puzzles? Yeah, that was quite arm wavy. I'm not entirely confident. Okay, so the question was basically the end of it was a bit rushed. Yes, the Merkel's puzzles is. I haven't given a proper full description of it. I'm not entirely brushed up on it myself. Yeah. It's important to realise that Merkel's puzzles, whilst a very interesting historical example, and actually quite interesting from a sort of theoretical point of view, as the best you can do without having to invoke fun maths, it doesn't actually have any real practical uses because of this terrible time complexity where you end up with insanely difficult keys. How does it feel to be the new Secretary of Cybersec? Oh, have they released it? Well, I suppose. Yeah, yeah, no, it's great. Well done, Cybersec committee. Let's go. In fact, probably everyone watching is on the Cybersec committee. That's great. Okay, well, anyway, for the YouTube video, I think I will end it here. I'm gonna float around Discord. Next week, I shall be covering. I'm not entirely sure. Probably something like probably symmetric, maybe public. Where I'll show you how we can use the uncrackable cipher in a way that's actually useful at the cost of losing the information theoretical security. Goodbye.